Hi everyone. We're going to start working on section 1.8, which is the second part of the fundamental theorem of calculus. This is really big stuff. It ties together a lot of what we talked about in Calc 1 and the beginning of Calc 2. So this first activity is a preview activity, which is like your warm-up. So please pause, work through this, check back in, make sure that you've got the first three right here, and then we will continue. So this kind of lays the groundwork for what we're about to do. Okay, so first is just a basic sketching the antiderivative. So if I'm looking at little f and I want to sketch its antiderivative big F, specifically big F that goes through 0, 0, what I can say, I don't need it to be very super accurate because I don't have any scale on this, but I can say that F is always positive, which means big F is always increasing. I can say that little f at first is getting more positive and then getting less positive, so big F should have an inflection point. So basically here, if I wanted to summarize f prime, it would be positive and negative. So little f increases till it hits its peak, then it decreases, which means its derivative is positive till it hits this peak point, and then negative. Which means big F is concave up and then concave down. I don't know why that didn't get an O. Okay, so my function is always increasing. It starts off concave up, ends up concave down. The last thing I would say is that here F is really close to 0, so big F should be really flat. So we start off really flat. We increase and increase and increase, so more and more quickly until we hit this middle point, at which point we're going to start slowing down, and again at the end you should be flat or really close to it. So this is a pretty good sketch of big F. Okay, so keep this in mind. This is going to help us out later. That was like your warm-up problem. Number 2 and 3 are just kind of a little prompt on some stuff that people get a little tangled in. So just on how much does the variable matter, basically. So if I give you this function, it's a quadratic function. First thing I ask you to find is what is m of 0? And the answer is going to be 0 plus 0 minus 1, which is negative 1. Similarly, if I ask you for m of 2, I'm going to get 5 times 4, which is 20, plus 3 times 2, which is 6, minus 1, so 25. Okay, so far just warm up for the warm up, really. If I then ask you what is m of big T, I'm just asking you to plug in big T wherever you see the x's, and I get this. And here's the really important follow-up question. Do the graphs, are they different functions? If I were to graph m of x and m of t, would they look different? And the answer is, unless you have some weird relationship between x and t that isn't stated here, no. If you graph m of x on an xy plane and you graph m of t on a ty plane, they should look identical. So if you're trying to graph m of t on the xy plane or m of x on the ty plane, that might get weird. But as long as we're looking at these, replacing the variable and changing the axis to match that, there should be absolutely no difference. Oh, do I want to try and say what this graph looks like? It's a parabola that opens up. Can I just say that much? Let's pretend it looks like this. And it would look exactly the same. That doesn't look exactly the same, but pretend. So changing variables is not a big deal unless there is some very specific relationship between your new variable and your old. Then you have to be careful. That's what 2.1 will be all about, is substituting out, making a relationship between variables. But here, same exact function, different label on the axis. Okay, with that in mind, if I gave you, in fact, I'll give it to you. I don't know why I don't just give it to you here. Let's say that the integral of h of t from 1 to 5 is 3. So we have some function h. We know the area, the sum of areas under h between t equals 1 and t equals 5 is 3. can you say what the integral from 1 to 5 of h of s ds is? And can you say what the integral from 1 to 5 of h of s dt is? And this ties right back into what we just said. If I am integrating h of t with respect to t, let's say h of t looks like this. And this is 5, and this is 1. T, y, h of t. If I tried to graph h of s with respect to s, it should look exactly the same. All I've done is change the name of the variable. I have not changed the shape of the function at all. So these two areas, even though I labeled one with an s on the horizontal axis and one with a t, areas should be identical. Please forgive the fact that my pictures are super wonky. So the answer here is yes, it would also be 3, or whatever it is. As soon as you start trying to integrate h of s with respect to t, that's when you can't make any assumptions. Maybe we know something about the relationship between s and t that makes that possible, but I certainly can't assume anything about it. So not going to claim that I know the value of the integral of h of s with respect to t. So some of this really helpful for this section. It's also looking ahead a little to the next section. Okay, so keep these in mind. I'm going to separate off the next example into another video. Thanks for watching.